Hello, welcome to Z Talk. In this session, let's talk about the mechanism of scheduling on Kubernetes. More specifically, I want to talk about the relationship between pods and nodes, and how do we restrict what pod to be assigned to what node. Basically, there are three key concepts here that we need to understand in order to figure out how does Kubernetes scheduler work, which are Taints Toleration and Node Affinity. I know these terminologies could be a bit confusing in the beginning, so that's why I'm going to spend some time here to explain them in detail about the differences and walk you through how do we use them all together for our use cases. All right, let's start with taint and toleration. So taint and toleration are typically used to set restrictions on what pods can be scheduled on a node. But remember the difference here. Taint is specifically applied on nodes to restrict pods from being scheduled on these specific nodes. On the other hand, toleration is specifically applied on pods to allow specific pods to be able to place on the previous tainted node. Right? So let's pause it here a little bit. I guess it already sounds quite confusing, right? So to help us understand better, let's take a look at the graph I drew. I guess visualization could be helpful to memorize how do we use it up together, right? So let's focus on the graph on the left-hand side first. This guy. We got a simple Kubernetes cluster for this scenario, which is composed of 3 nodes, 1, 2, 3, with exactly the same configuration. And there are 4 pods, A, B, C, and D, are being deployed to this cluster. All right? So when the pod is created, Kubernetes scheduler tries to place it to an available worker node, as we know, right? By default, there is no any limitations or restrictions in place such that the scheduler, following the strategy of round robin, is going to distribute pods to the worker nodes in the cluster equally, to balance the load, which is exactly what these first graph shows. So pod A is going to be placed on node 1, and pod B is going to be placed on node 2. C is going to be placed on node 3, and following round robin, pod D is going to be placed back to node 1, right? That's quite straightforward, simple, right? And now let's change our scenario a little bit. Let's move to the second graph on the right hand side, this guy. And obviously you can see the difference here. Node 1 looks much bigger than the other 2 nodes, right? So that's the change we made here. Now we got, for this specific scenario, we got a dedicated resource on node 1 because it's configured as the more powerful box compared with the other 2 nodes here to host a specific application. And let's assume, or let's say pod A and pod B are the components of application X. So in other words, for this scenario, we'd like only pod A and pod B that belong to application X to be scheduled or to be placed on these node 1. So now, due to this specific scenario, we cannot just follow the previous round robin strategy anymore, obviously, right? We're gonna have to put some restrictions in place to fit the requirements. That's basically where we're gonna depend on taint and toleration that we just talked about. All right, so here's the plan that what we're gonna do here. Firstly, so here, this is the first graph right here. This is the original scenario, so which following round robin, pods will be distributed to the nodes equally, right? Following round robin strategy. And now with these new requirements we just talked about, what we have to do is we have to put in some restrictions on both node and pod side to fit our requirements. So that's what we're gonna do here. So let's focus on the graph in the middle right here. So step one, so we're gonna place a tent of red, like I pen here, tent of red on node 1, such that once these tents takes effect on node 1, no pods is going to be allowed to be placed on node 1, because by default pods does not have any tolerations on pens, right? So that's why no pods can be placed on node 1, right? So that's pretty much, we accomplish half our goal by restricting pods from being assigned or scheduled on node 1. But we're not done here yet. So in order to have pod A and pod B be able to be placed on node 1, so we have to put or apply a toleration of red on pod A and B then, so that A, like the back to the last graph on the right hand side here. So once we applied the toleration on both pod A and B, and once the toleration takes into effect, A and B are now allowed to be placed or to be scheduled on node 1. That's pretty much our goal, right? Here we go. This is the syntax of tent command that we're gonna issue, to apply to node 1, right? kubectl tent nodes, and then followed by the name of the node, and then followed by a key value pair. And the last piece is called tent effects, which basically means what's gonna happen to pods that do not tolerate this tent. And for the last piece, we got 3 options available to choose, which are no schedule, prefer no schedule, and no execute. And follow the previous use case, and here is the specific command we're gonna issue. As we know previously, I called application as application X, right? So going forward to fit the graph or the pen I put here, so I will call the application as red. So that's pretty much the tent we're gonna apply to node 1. So kubectl tent nodes, and then followed by the name of the node, which is node 1, right? And the key value pair is gonna be app equals red. And the tent effects we're gonna use as no schedule. So going forward, once these tent commands takes effect, only application red, which is composed of pod A and pod B, is allowed to be scheduled on node 1. All right, and here I use the tent effect as no schedule. Basically, no schedule means that no pod will be able to schedule onto node 1 unless it has a matching toleration, which means we must apply the toleration of app equal red on both pod A and pod B before they're able to be scheduled on node 1. Right? That's the change we made on tent, which is on the node side. And then let's move to the second change, tolerations on pod side. So to add the tolerations on pod, what we're gonna do is we're gonna modify the pod definition YAML file right here. So here we're gonna refer the tent command that we just issued like this. And as you can see, in the pod definition file, I just add a new section of specification of tolerations, and following this exactly same thing that I defined in the Taint command, which is, you see, tolerations, key is app, operator is equal, and value is red, right? And effect is no schedule, right? It's pretty simple. Now let's dig into a little deeper about the Taint effects using the same example here. Let's start with the first graph on the left-hand side here. This is basically the first simple scenario we discussed about in the beginning of this session, where we did not have any taint or toleration in place at all, so that the scheduler balanced the load across the 3 nodes equally, following the round-robin strategy, right? And then let's move on to the graph in the middle here. We got extra requirements where we had to apply a taint on node 1 and set the taint effect as no schedule, because we had a requirement of restricting node 1 to hosting application red only, which is composed of pod A and pod B. And meanwhile, we've also applied toleration on both pod A and pod B. All right. By the way, I've explained the no schedule taint effect like 2 minutes ago. So let's change the taint effect to no execute here, because I want to introduce this new scenario to explain the limitations on taint and toleration. All right. So basically, if a taint with effect no execute is added to a node, then any pods that do not tolerate the taint will be evicted immediately, which in our case, pod D here, which is currently running on node 1, is going to be kicked out of node 1 once the taint takes effect. On the other hand, pod A is going to continue to run as it is because pod A has been applied the toleration. All right, and now let's take a look at the other 2 nodes, especially node 2, and we found a problem where pod B has already been running on node 2, which is the problem, right? Like what I brought in the third graph here, I was saying, what about pod B here? Because as our requirements, pod A and pod B, which belong to application red, are supposed to be running together on node 1 only, right? But apparently, just taint and toleration did not fulfill these requirements. So that's because that's the toleration I wanna bring up here as a note here. Taint and toleration are only meant to restrict nodes from accepting certain pods. However, it does not guarantee that those specific pods will always be placed on the tainted node. So that's the limitation. So due to this limitation, how are we going to deal with it to accomplish our goal of restricting pod A and pod B from being placed on other nodes but node 1? That's basically node affinity comes into the picture. All right. Let's talk about node affinity. Basically, node affinity ensures pods are hosted on specific nodes, which is exactly what we needed here, right? In general, there are 2 steps to set node affinity. Firstly, we're going to label the nodes where we want to host the specific pods. In our case, let's label node 1 as size equal large as the key value pair, because we know node 1 is bigger than the other 2 nodes to, differentiate node 1 from the other. All right. And then the next step, by the way, I wrote down the specific command that we're going to issue to label node 1, which is kubectl label nodes and then followed by the name of node, which is node 1, and then followed by the key value pair of the label, which is size equal large. All right. And now we're going to move to the next step, where we're gonna add node affinity specification in the pod definition YAML file. More specifically, the highlight section here from line 14 to 21. I guess you already noticed there is a long property called required during scheduling, ignored during execution. Let's put it on hold right now, because this is a key property that I'm gonna explain in detail in the next slide, like in 2 seconds. All right. So now, as of now, let's just focus on the node selector section here, which basically, the information basically comes from the first step where we set the label. As you can see here, the key is size and value is large. That helps the pod to identify the nodes where it's going to be hosted on. All right. All right. Let's move to the next slide. Here we're gonna talk about that long property. As of now, when the pods are created, all those rules that we configure, like node affinity, taint and toleration, are gonna be taken into consideration, and pods are placed to the right node, right? However, imagine what if node affinity can't match a node with a given expression. For example, what if a label size that we placed on node 1 were removed after pod A and B were scheduled on node 1 as we planned? What's going to happen on pod A and B in that case? Well, this question is answered by this specific long property of node affinity type. All right. So basically, the type of node affinity defines the behavior of the schedule with respect of the node affinity and the state in the life cycle of the pod. There are 2 states in the life cycle of a pod when considering node affinity: during scheduling and during execution. During scheduling is the state that a pod does not exist and is created for the first time. We have no doubt here, when a pod is created, node affinity is going to be taken into account and the pod is scheduled to the right place. But consider, what if we forgot to label node 1 as size large? That's where the type of node affinity comes to play. If we use required type, the scheduling is going to mandate the pod being placed on the node with a given affinity rules. So the pod is not going to be scheduled if the scheduler cannot find a node that matches the rules. Typically, this type will be used for cases where the placement of the pod is crucial. On the other hand, if the pod placement is not such a big deal, then running the workload itself, we could just set the type as preferred, which means the scheduler is going to ignore the node affinity rules in case there's no matching node being found. And the second part of the property is the other state during execution. During execution is when the pod has been running and a change is made in the environment that affects node affinity. Like the example I mentioned earlier, consider what's going to happen if the size label were removed out of node 1. As you can see, both 2 types during execution have set as ignored, which means the pod that is already running on the node is going to continue to run as it is, even though the label is removed. That's pretty much this long property, the type of node affinity all about. All right. All right, demo time. In this demo, I'm just going to quickly walk you through the 3 terminologies regarding scheduling we learned about using a simple BusyBox image, right? And again, please thumb up my video if you think it's helpful, and subscribe my channel. And more importantly, please feel free to leave comments if you have any questions. All right, let's hop on to the demo. All right, here I spin up a 3-node Kubernetes cluster dev environment ahead of time. It's actually still the same environment that is set up via Vagrant for the previous session about Elk-Stack. If you're interested in how did I set up the dev Kubernetes cluster via Vagrant, here's the link to the previous session, so feel free to take a look, right? So the first thing I want to verify is the first simple scenario we discussed about in the PPT slide. Let's check out how does Kubernetes scheduler distribute the pods by default. To verify that, I'm going to quickly spin up 4 random pods, like the use case I described in the PPT slide, right? So kubectl run pod A, let's use the image Nginx. All right. Okay, so pod A was created. So let's check out the detail by kubectl get pod white. Here we go. So let's just ignore these 2 pending pods here because they're nothing to do with this session. So let's focus on the first pod, pod A, which was the one we created just now, right? And as you can see, pod A was scheduled on worker node 1, right? So let's continue by creating like another pod, kubectl get run pod B. And this time, let's use image like BusyBox. All right, here we go. All right, so pod B was created as well. And same thing, let's check out detail here. As you can see here, pod B was created and it was scheduled on worker node 2. This is exactly what we're expecting, right? Because out of box, the scheduler gonna distribute the load equally across the nodes following the round robin strategy. So if I spin up another pod, it's supposed to be placed on worker node 1 again, right? Let's verify that. So I would do kubectl run pod C and image equal let's see, let's spin up another BusyBox image. Here we go. All right, pod C was created, so let's check it out. Kubectl get po wide. All right, see here, pod C was scheduled on worker node 1. So the last pod, so let's spin up pod D, and pod D is supposed to be scheduled on worker node 2. So let's verify that. Here we go. See, pod D was scheduled on worker node 2. Right, so that's exactly what we learned in the PPT session. So this is following the round robin strategy, right? So let's move on to the second scenario with the new requirements. Let's taint a worker node 1 and verify the second scenario we discussed about. All right. The requirement was to dedicate worker node 1 to hosting application read only, which is composed of pod A and pod B, right? And the current situation is that pod B is running on worker 2, actually, and pod C is running on worker 1 on this dev environment. So let me apply toleration on both pod A and pod B first. By updating the pod definition file here. Let's start with pod A. as you can see, I've added the toleration section here. The key value pair is going to be app equal red. And regarding the taint effects, I'm going to set as no execute. Remember the effect no execute? The pod will be evicted from the node if it's already running on the node, right? So that we can verify once the taint on worker 1 takes effect. Number 1, if the pod C that's currently running on worker 1 is going to be killed because it doesn't have toleration applied, right? And number 2, if the pod A stays as it is because we apply the toleration here. All right, that's the plan. Let me exit out and apply these toleration to pod A and pod B by kubectl apply pod A and kubectl apply pod B. All right, now let's verify by kubectl describe pod A to confirm the toleration here. The toleration app equal red, no execute, has been applied on pod A. All right, so cool. Now let's apply the taint on worker node 1. Kubectl get node. So let's do kubectl taint nodes and the name of the node, which is k worker 1. By the way, let's check the current status before we apply the taint. So here kubectl get pod, right? And we saw 4 pods here, A, B, C, D, and A and C are running on worker 1, and B and D are running on worker 2, right? So now let's apply the taint on worker 1. Kubectl taint nodes k worker 1 app equal red, no execute. All right, the taint has been applied to worker 1, so let's check the pod status one more time. All right, as you can see, pod C is gone, right? That's exactly what we're looking for, because as I explained earlier, pod C should have been killed because pod C does not have toleration applied, right? And pod A stays because pod A, we just apply tolerations ahead of time on pod A. All right. That's pretty much the second verification I want to demo here. And the last part is going to be placing node affinity in place, because as we can see here, the problem, pod B is still running on worker 2, which is the limitation we discussed about taint and toleration, right? So we are going to apply node affinity so that we can restrict pod B and pod A on worker node 1 only. All right, so let's do that. All right, step 1, I'm gonna attach a label on worker node 1. Here we go. Let me just list out all the labels attached on worker node 1. And as you can see in the end, I just attach a label called size equal large to worker node 1, right? And then I'm gonna update the pod definition file on both pod A and pod B to include the node affinity section, right? So here we go. And as you can see, I've added the affinity section, and take a look here. The expression is pretty much based on the label that I just attached on worker node 1, right? As you can see, size equal large. And now the current status of pod, so pod A is running on worker 1 already. So what I'm gonna do, I just gonna apply the change here, but it's actually gonna be no change at all because pod A is already on worker node 1, right? So I just do a kube cuddle apply A. So what we want to verify here is pretty much pod B, because pod B is currently running on worker 2. So I'm gonna do kube cuddle delete pod B, and then I'm gonna reapply pod B by kube cuddle apply pod B. Alright, now let's check out the status of pod by kube cuddle get PO white. And as you can see, pod B was placed on worker node 1, right? And let's do one more verification by spinning up another pod, kube cuddle get actually run pod C, and pod C image equal busybox. Alright, and spin up another one. Let's call it pod A, B, C, D, E. So now, because the tent has been applied to worker node 1, so all these two pods that we just spin up, pod C and pod D, are supposed to be scheduled or placed on worker node 2, right? Let's double check by kube cuddle get PO white. And here we go. Pod C and pod E were all scheduled on worker node 2. Alright, that's pretty much what I want to share for this session. Again, thanks for watching, and I'll see you next week.
Alright, thank you for watching my video. If you think this video is helpful, you're more than welcome to leave any comments. Remember, thumb up, subscribe my video, and also hit the notification bell. See you next time.